It's raining.
In the table, I found a direct
No,
solution
what
for
is
this.
Raining?
Really?
Yeah.
But no more, right?
Yeah.
Oh, yeah.
What name
I
is
did
rain?
step by step by taking the
Ah.
bus.
What
Practice
name?
and
practice, yeah.
The rain, but no more.
What type of raining is
Same
this?
answer.
Okay.
I don't know.
This is a standard one, I think.
And I
In your
Same
country,
answer, exactly.
what they say this type of rain?
No, sometimes it's like
Yeah.
no rain.
I
The
didn't,
name is different.
I didn't take
Yeah.
for the practice.
but if you got
In our country, it says Sing Band.
table.
Yeah.
Are you left swing set?
I'm not interpreter. I'm not
If I can remember. We have to operate, I want to.
If you can remember that, it's okay.
Hey, how are you? Oh,
I don't know.
1:05 p.m. Friday. Yeah. Cool.
Friday, 1:05 p.m. Okay.
Here,
Come
right?
on, good
Yeah.
side.
Yeah, yeah.
Yes.
We're a meeting in
Chase
here.
me.
Okay. So,
Cool.
yeah, yeah.
You didn't open the chase part.
I will come.
You should have gotten an email.
Yeah.
You should.
I didn't have my social security now, so I had to go through the them to give the new one.
If you didn't get an
If I
email,
want
that's
a credit
because
card
it's
also.
only graduate students.
I don't know.
That's-
You have to
that's
get
not
to
how
the
I-
office now, right?
I don't know.
Uh,
That was kind of hard until
you
Gamini.
to get from the
Dr.
ISS.
Gamini was like, oh, all grad students.
That the form
Plus
for
you.
Yes, you can.
And plus like one other from outside the department.
Your same interest.
Except for some graduate classes.
You went there.
Around
Yeah.
Yeah, after getting
Try.
to allow to sit in the.
We're open.
What the Holocaust?
Yeah.
I
We
got
all
the
need to have
application.
our picture taken.
About 20
Everybody's good, right? No, I can bring paper. Yeah.
I just had to make sure that's
That kind of paper, good grief. I thought you were leaving to get the paper you get for exams for a second, and I was like, what?
What is pop quiz?
Yes, surprise quiz.
It's too early for that stress.
Listen.
The disclaimers that they clean like sides of the building with.
Squeeze.
Yeah.
All right, what I want to do is continue with the applications of Toshiba's detail. We already did some problems last time. So today what I'm going to do is first say a few things about the principal of integration and maybe develop Jordan's lemma and also maybe solve a problem where we have multi-valued function in a function integration. Okay, so that's what I want to do. so, we may have an integrand which has singularity or simple pole on the real axis. If we have an integrand with simple pole on the real axis, this is what we want to do. Let us say we are trying to evaluate the integral of this form. Clearly, this integrand has a simple pole at x equal to x0. And Cauchy residue theorem applies for a closed contour, right? So, so in applying the Cauchy residue theorem, if I have to use a closed contour, what happens is the contour that I would normally choose is something like this. Minus r to plus r, x equal to x0, and that is, we got a simple pole, so we are trying to avoid that part of it, and then we are going around this. Okay, so C1 is a small semicircle around the point x0. So the way to think about this is as though, this is how in most of the time, as though we are pulling this, we add a small imaginary quantity to x0, and we pushed it to x0 minus epsilon. Okay, so it's not, that's another way of thinking about this. Okay, so this way it's not in your path. If it was minus infinity to infinity, if I did not do it, you got a pole here, so it's going to blow up, right? So we are trying to avoid going through x equal to x0 by drawing a small semicircular arc around this. Alright, so of course the Cauchy theorem, residue theorem is always applicable to a closed contour, okay, that whatever it is in this case. Okay, we will be applying something, we have to choose a contour like this and try to, from there, we try to extract out the information on this infinite integral. That's how we do. And so this closed contour, it depends on the integrand. You may have some singularities in the upper half plane. Then you must have, if you had, of course, the right hand side will be 2 pi I times the residue of all the poles. I'm going to call it J because this I is imaginary. Residue of all the poles or singularities in the upper half plane. This is a theorem. If you didn't have anything on the upper half plane, you could have a function like that. We'll do an example of that. If that happens, then the right hand side is 0. Okay. So supposing, let me consider a case, the only singularity is on the real axis for this integrand, and there is no other pole. Let's say it was something like exponential of ix or something like that. It has no pole. Okay. Then my right hand side would be 0. Okay. Yet when we try to calculate this, there's a contribution. We will try to evaluate such integral in the limit r going to 0 and big R going to infinity. Big R is that, and small r is, let's call it delta at this point. I just want to call it, okay? So if I call the radius is delta, then this point is x0 minus delta, and this point is x0 plus delta. Okay. So the radius here is delta, or the small circle is delta. So this contour integral, if I had nothing on the upper half plane, I will write it as minus r. I'll break the contour into different parts. I'll go from x0 minus delta. I'm traversing on the real axis. first. It is that piece. Then I have on C1, it's now upper half plane, so I put the variable z. Okay, this is on C1. Okay, C1 is this circle. Okay. Then I go from x naught plus delta to plus r. I'm still on the real axis, so I will write it as x minus x naught dx. Then I go to the upper half plane on the bigger circle, f of z, z minus x naught dz. And the right hand side is 0 because on constraint case, there are no, if this is 0, there are no singularities on the upper half piece. Let us see. There are no singularities by the Cauchy's first theorem that we, not the Dirichlet, Cauchy's theorem for, it's an analytic in the upper half plane, then the right hand side has to be 0. Now, so what is z on this circle? The value of z here, the variable z, you have to understand what is here, what is here. How do we represent the variable z? On C1. Radius of that is delta, let's say. See, it's not centered at 0, right? So what the variable z minus x naught, the variable is delta is the radius I theta. Is this clear? Previously we had it centered 0. Here it is, at x naught. Wherever it's centered, wherever the circle is centered, you have to take that, right? Z minus x naught is delta A theta. So z there is x naught plus delta E I theta. This is. All right, and then you're going from what? Pi to 0, right? So you're going in the clockwise direction. So when you change variable from z to theta, you have to go from pi to 0. Okay. So let's do that. And then let us for simplicity, I'm talking in general at this point. Suppose my function f of z is such that, the contribution from the upper half, the bigger C2 is 0. Let us say a case like that. When we come to specific problem, these things will become clear. So, of course, there it is, z is, it's also said z minus x naught is capital R I theta. And in all these problems, we will evaluate such an integral for r tending to infinity. The bigger circle is going to, infinity, the behavior of it, and we want that to go to 0. I mean, depending on the function, we'll talk about Jordan's lemma in this connection. And the smaller one, of course, we want to shrink it so that we have the principal values as close to the original integral. So we want to shrink the delta, small delta to 0. So this integral we want to calculate in the limit delta tending to 0. This contour integration over the bigger semicircle, we want to calculate in the limit of tending to 0. Alright? Alright, what is, if this is the case, on C1, what is f of z over z minus x naught dz? dz is, x naught is a fixed point, so it's delta I theta, I delta theta. So this integral is nothing but I, you're going from pi to 0. Okay. This is nothing but value f of x naught plus delta I theta. And dz is this quantity. Alright. And z minus x naught is delta I theta. this is nothing but delta theta from the definition, the way we are defining it. So what we have is, this will cancel
Where did that extra I come from?
dz. Extra I came from here.
Isn't that in there?
No, but you have to understand this, okay? This will keep on coming, okay? Z is equal to x naught plus delta ei theta, right? dz when you take, this is constant, so that is 0. Okay, that's radius. So this is nothing but delta exponential of I theta, the I delta, right? So
Yes.
this is,
I see that, but there's an extra I in the front too.
oh, okay, that is not there.
Okay, that's what I was
Yeah.
confused about.
Okay.
I understand.
I must have, yeah, that's, yeah. No, this I must have already put it up or something. Okay. So dz is coming from there, that I is coming from there, okay, so that's cancelled. For delta tending to 0, this is becoming pi to 0, value of the function of x, this is 0, okay. So I have a I, delta theta, okay. So this is nothing but negative I pi of value of the function at the numerator, right, I mean of this integrand at x equal to 0. So whenever you have a, okay, so this, and let us for the, right now, you know, we don't know what the integrand is, so let's assume this other one is 0, okay? But what I want to say is this part of the integral is always negative I pi times, as though you calculate the residue of this integrand at z equal to x naught, right? Because that's a simple pole. Then it, you know, you're calculating z, you're multiplying z minus x naught, it will cancel, for z equal to x naught, it's fx naught, okay? So it is, this quantity is nothing but the residue of this entire integrand at z equal to x naught. Okay, that's another way of interpreting what that quantity is. Okay, so the principal value integration is the following. So we have this, supposing we brought these two terms together, and we're putting r equal to infinity and delta tending to 0, then these two terms together is what we call as principal value integration. Principal value is, so r tending to infinity, what we have is principal value of the integrand, because we're eliminating a small portion of the real axis, right? That's what it means. Okay. Minus I pi fx naught equal to 0, or the principal value of the integration of this integrand is supposing I had nothing on the upper half plane, is simply I pi times fx naught. I've taken that to the other side, or you can write it as I pi times the residue evaluated at x equal to x naught. So residue of this whole integrand, right? I mean that's why you get fx naught. Okay. And of course, if you had more singularities on the upper half plane, the principal value integration in that case would be the following formula. So this is on the real axis plus 2 pi I times residue of all the singularities, you know, or whatever, all the singularities, the n singularities, let's say, on the upper half. So this is residue of the integrand on the upper half. Of singularities in the upper half. this is the residue of the integrand on the real axis. For the pole, or say right in this, in this case of the simple pole on the real axis. Is this clear? Okay, so I want to mention something that you might have already seen in quantum mechanics or will be seeing. Let me just make a connection of this with what we do. Alright, this as though we had, shared it on the, x naught, we pulled it, we put, it was on the real axis, we just, moved it into the lower half plane, okay, and we are trying to calculate this integral in the limit epsilon tending to 0, okay. So you will see this, and in fact, what I want to show is, this is the expression that, most importantly, I wanted to show. You might have seen, or you might have used it already. An expression like this is written as principal part of 1 over x minus x naught minus I pi So I have a pole on the real axis, right? There's nothing asking, I could have pushed this to upper half plane too, right? I could have done it like this, and I could have traversed in this, like this also, okay? I mean, there's nothing which is stopping me from doing that to evaluate. Whenever you have pole on the real axis, you could have done it that way too, okay? So in this case, you pushed it to x plus, that one became that, the other one became that, okay? X naught plus I epsilon, then you would have had a plus sign here. You will come across all these things. This expression, have you encountered this before? To why we write, 1 minus x naught plus I epsilon, okay? You will always see something like a principal part of this part of the denominator, and then there will be Dirac delta function, I pi times the Dirac delta function. This is nothing but, this is what we have proved right now, right? I mean, so if I had this expression, I multiply by fx and integrate with minus infinity and plus infinity, this is what I should get, right, this expression. So that's where you get this expression from, right? So if you see, suddenly, mostly in scattering theory, you will come across such expressions. So in principle, this could be minus plus, right? So accordingly, it will be minus plus. Okay, so both these expressions are possible. So what they have done is, if you come across that, what they have done is, if you have a pole on the real axis, it's been pushed either to the lower half plane or upper half plane so that you really could, in some sense, this is what they have done, and then try to evaluate. So that's another way of visualizing all these things. Okay. So I just want you to understand the different forms of principal value integration that might come even in quantum mechanics. These two expressions will come quite often in quantum mechanics. You might have used already such as this one definitely might have used already, I think. Okay, so that is just to, if you see that, you know it's something coming from principal value integrations, okay? You know, something was, singularity was on the real axis. Okay, let's try to do an example so that you understand what we're trying to do. So let's evaluate this integral, the real integral, right? I mean, so we want to use Cauchy-Restier theorem for evaluating this real integral. Okay. So the first thing that you notice is what? I mean, we always want closed contour, right? I mean, so whenever you have an integral, first examine whether it can be written as an even function, okay? And if that is the case, then I know I can go from minus infinity, minus r plus r and close the contour. So this is an even function, right? Because this is odd, so it's an even function. So I can write this as half of 0 to infinity sin x over x dx. Alright? Now, yeah.
I thought it had to go from negative infinity to infinity to do that.
Oh, sorry, that's what I'm trying to. Minus infinity, yeah. Half of this, yeah. Half of this, yeah. That was the point. Yeah. Now, so it's still a real integral. Okay. Now, what did I say? That we always have to, whatever integral you have, because Cauchy's residue theorem is for complex variables and complex functions, we approximate this to whatever, not approximate, I mean guess the closest complex, integral of this, of the integrand. So what do we write for the numerator in this case? So this is the integral, that real integral that we have to calculate, okay? And we wrote it this way. The next step is, whatever it is, x is still here a real variable. I want a complex variable.
Replace it with z.
Hmm?
Replace x with z.
Normally yes, but in the case of sine function, I want to replace it by exponential iz. Okay, denominator is z, that's fine. Okay, so then I will, from there, that's what I'll evaluate. From there, I'll somehow extract out my sine of x over x eventually. Okay, so this is what we have to calculate. But the integral using Cauchy's theorem, residue theorem, what we are going to evaluate is this integral. Whatever, if I know how to calculate this, imaginary part of that will give me sine, we will evaluate this and somehow our goal is to extract out this number, this integral. Is this clear? Okay. So don't put sine of z, okay, that would, that is only real. So always take, whenever a sine or cosine, that is the complex integrand that you calculate. So that's the first step. Because if you do that, you get what we want. So we want to calculate this, right? Now, this is similar to the principal value integration. Z equal to 0 is a simple pole in this case, right? And if I choose a contour which is going like this, as we did just now, in this case it's centered around z equal to 0, not x naught, z equal to 0. So this is minus r, this is plus r. Let me call this as, if this radius was negative r, let's say negative r plus r. uh, do I have in this case any, for this integrand, any singularity in the upper half plane? My integrand is exponential iz over z. Where all it's blowing up. Only at z equal to 0, right? There's nothing else in the upper half plane. Alright, yeah. What was your question?
Like, what would happen when you made R go to infinity, but I guess we'll see that in a
We
second.
will, yeah, let's see that in a minute. So I got nothing in the upper half. There are no singularities in the upper half plane, okay? So this integral, you know, for this figure is actually 0. Right hand side is 0. So I don't have to calculate residues and stuff like that in this case. So you have to always, the Cauchy-Residues theorem says is whatever contour, closed contour you have chosen, if inside that contour you have a singularity, then you have to calculate the residue. That's the important part you have to remember. Now, okay, this is fine. So as usual, I'll split the C into different parts. So I'll have minus negative R to negative R. So you are on the real axis at this point, right? And then on C1, because now you have gone above the plane, I have to have Iz over Z, dz. Okay, and also you're going from pi to Z and all that. We'll come back to that. R2 plus R. I'm back on the real axis. Okay, I'm on this part. And then I'm on C2. So since I have a real problem, I can now evaluate this integral, right? I mean, it did not. And my right hand side is 0 because no singularity in the half plane for this integral. Alright, so we will, as usual, we'll put R tending to infinity and small r going to 0 and evaluate the integral. And what is the contribution of this integral now? On C1, what is it? If you want, you can put Ri, you know, all that stuff, Ri, e to I theta and evaluate. You know, that's how we did it, right? I mean, or we already derived the expression what it is. You know, the principal value integration around that small circle is nothing but negative I pi times the residue of this integrand at z equal to 0 or x equal to 0. Right? So what is that? I mean, if you didn't remember that, you just, you know, you will go and substitute z equal to r exponential of I theta, right? I mean, you just calculate that, and you know, you're going from pi to 0, so you know how to calculate that. Pi to 0, exponential of I, IR, you know, cosine theta, cosine theta, it doesn't matter. dz is r. And z is exponential of theta, so r and r will cancel, so all these things will cancel, right? So in the limit r tending to 0, this is 1 anyway, so this quantity is nothing but negative r equal to 0, this whole thing is 1, so, and so all you will be left with is equal in the limit r tending to 0, this is the only term you have. So this is nothing but negative I pi at this point, right? Is this clear? Which is same as whatever I wrote previously, negative I pi residue of the integrand at z equal to 0. Since it's simple pole, you multiply with z and evaluate the integrand for z equal to 0, which is 1. Okay, so you can do it either way. But it's always best to go back to, where it came from, so it's, all right. So, so we are also letting r tending to infinity. So what we are getting is principal value of this quantity, or this integral, minus I pi. I do have this, okay. We need to check what happens to this integral r tending to infinity, and right hand side is 0. Okay. So this is like a Fourier integral, okay, and I'm going to prove this in a minute for you. It is like exponential of Im x, Im z, f of z. F of z for you is 1 over z. So such Fourier integrals will be 0 in an infinite semicircle. I'll prove that to you. That's equal to 0 based on what is called as Jordan's lemma. So you cannot arbitrarily, not for every integrand, it will go to 0. Okay? You have to give the reasoning. And last time you saw, if a function f of z, decays to 1 over z square or high powers, it will become 0. Okay? We have to check the condition. Z times f of z tends to 0. That's one condition. What we did was, if the integrand is such that z times f of z becomes 0 as r tending to infinity, yes, it will go to 0 in the upper half. Okay? But in this case, that's not the case, because if I put z times, f of z is exponential, it looks, it's not satisfying that condition. Okay, that's why we need to understand this, and that will come through Jordan's lemma, which I'm going to show it to you why that is 0. But for the moment, because our goal is to evaluate this, so I want to show you what that is. So what we have is principal value of is I pi. This is what we have proved, right? Which is nothing but principal value of minus infinity to cosine of x dx plus principal value of, or I times principal value of sine of x over x dx is equal to I pi. This is what we have. All I've done is just split the expression I into sine of sine. Now, since this has no real part, so what we have is, I have to compare the real part of the right hand side with the real part of the left hand side. That is 0. So I get that as a bonus, that integral. And this one is, so what I get is negative infinity to plus infinity sine of x over x dx is pi. This is by comparing the imaginary forms. Parts of right hand side and left hand side of the equation. Right? And we also have the other one, of course, minus infinity to plus infinity cosine of x over x dx equal to 0, because the real part is not there, plus 0, right? So I'm comparing this, that should be identity equal to 0. So what I have is then this integral, which is what we had to calculate, is nothing but half of whatever I calculated. This is what we have calculated, right? Which is pi. So this integral is nothing but pi over half. The real integral that I have to calculate is pi over half. Is this clear? All right. So, so all we did was we were asked to calculate real integral, infinite real integral. We first converted that into infinite domain minus infinity plus, if I can do it. Then I can choose a semicircle like that. And I chose the complex analog of these functions, of these real functions, so that's why I put that. And so split the C, which is a closed contour, into different parts. Okay. First we are going along this real axis, upper half real axis, and then the bigger circle, that's it. And we have to make sure, based on whatever the integrand is, there may be problems where the right-hand side may not be zero, so then you have to calculate that. Okay. So this was a simple one where we have nothing, but we need to now understand why this integrand becomes zero here on C2. I mean, otherwise you have, otherwise that's not the case, right? Unless it becomes, there's no contribution from there, then only then we get that result. Is this clear at this point? Yeah. Okay. What it tells you is the following. If f of z is a complex function, analytic except for and maximum value of f of z tends to 0 as z tends to infinity.
Maximum value here.
Yeah, it is, we will always take the absolute value, and you'll see it in a minute, I'm going to show it to you. Okay. In the upper half plane, which is 0 less than or equal to argument of z less than or equal to p. So if this happens and then m is greater than 0, then this such integrals will go to 0 as z goes to infinity. Or r tending to infinity. The semicircle. Okay. Where gamma is a semicircle, in this case, gamma denotes a semicircle in the upper half of radius r. So it is less stringent compared to the previous case. Previous case, z times f of z had to be 0 as z, as z tends to infinity. So our example here, what do we have? We have exponential of iz over z dz, right? This is what we want to make. We want that to go to 0 on C2, right? I mean, that's the upper half plane in this case. My f of z in this case is 1 over z. It satisfies this condition. It goes to 0 as z tends to infinity. But we have to prove that this is true for the upper half plane. But previously we had, I don't know what example we did, I forget, but we had things like, more like, I think something like this, or z z squared, or something like that we had, or z cubed, we can have it, such problems. Definitely no problem, I don't need Jordan's lemma for that, because I have r exponential I theta, here I have r cubed, I have 1 over r squared, net r squared in the denominator of r tending to infinity, that will go to 0, right, when 0 to 2 problem in the integration. So that's not a problem for such integrals, or such integrands. All right, let's understand this. It's sort of, what you do is, we estimate these kind of integrals, right? And that's what we are trying to do. Okay. The upper limit of the integral that we're going to estimate. So let me call this I gamma is this integral. So whenever you have, think of this as a Fourier integral of a function f on c. All right. Okay, so z of course is nothing but r exponential I theta, same thing. dz is r exponential I theta, I d theta, okay. Maximum value of f of z, let's call something m, okay. So this integral in the semicircle is nothing but, it looks like 0 to pi, okay, exponential of I, n, r cosine theta plus pi r sine theta, and let me write down f of z dz. Z I can write it as r exponential of I theta I delta theta, right? So this I gamma is, at this point all I did was substitute for z, all that stuff. But what we're going to say is this integral I gamma is less than or equal to, because I need to, if the right hand, it's less than or I'm going to get the upper limit of this right hand side. So if the maximum value of f of z is m, I'm going to call it as mr at this point. And I want to take the absolute value of everything, okay, at this point. When I take the absolute value of everything on the left hand side, exponential of I times whatever thing is going to be 1. So I'm left with m r sine theta in the here. And already I've put the absolute of fz as m, so I've taken out. Absolute value of I theta will be 1, absolute I is 1. All I have is something like this. Okay, so this is the, so this value of the integral, the actual integral, has to be less than or equal to this quantity. Okay, where I have taken the absolute value of everything on the right hand side. Okay, that's all I've done. All right. Now, I can write I gamma as less than or equal to m times r. I can write it as 0 to pi over 2 of mr sine theta theta. In the 0 to pi, it is, it is even sine theta, right? I mean, so I can write like that. Now, what I'm going to do is, one more trick I have to do. I'm going to divide by theta and multiply by theta here. I can do that. Now, sine theta over theta, for theta tending to 0 is what? 1, right? Sine theta over theta, for theta equal to pi over 2, is 2 over pi. That is. So we know that it lies between now I'm estimating this integral. If this is convergent, you know, this has to converge. That's the argument. The lemma is that's what we're going to be doing. So this one I'm going to put the, since it's negative, I have to put the minimum value here so that I can calculate the maximum value. For sine theta or theta, it's bounded between these two values. I'm going to put minus 2 over pi. Okay, so I'm just estimating this. So I gamma is nothing but less than or equal to 2mr, okay, 0 to pi over 2 of exponential of theta nr over, put it as 2 times, is it right like that, 2mr over pi times theta d theta. And that's an easy integral to evaluate. And let's see, examine this integral. 2mr is nothing but an exponential of 2mr over pi divided by negative 2 n times pi. Theta, right? So this will be the upper half pi over 2 minus 1. Is this correct? So what this is, I gamma is less than or equal to, I can cancel this 2. So I have n pi, like that, over n, small n, and I can change the sign inside, 1 minus exponential of mr. This n is the maximum value of your function f of 0. And this m is that, you know, m here, this Fourier integral. Okay, so that has to be greater than 0. Okay, so one condition is m has to be greater than 0, because otherwise r tending to infinity, that will blow up. So, so what we have is this goes to 0 for those integrals for which n is greater than 0. So what you have is I gamma is less than or equal to pi m over n. And if m, which is maximum value goes to 0 as r tends to infinity, then this integral I gamma, you know, has to converge, has to become 0. So that is the argument. So any integral of this form, which you can think of as Fourier integral, right? Exponential I, that's how we write Fourier transform, right? X of kx, f of x, dx kind of a thing. So most of the Fourier integrals, when you calculate in the upper half plane, where m is greater than 0, and this quantity, now the condition is also on this one, it has to simply become 0 for z equal to infinity, okay? So then, that is Jordan's lemma. Then this, the evaluation of the contour, this integral, not contour, the evaluation of integral on C to the semicircular arc will go to 0, okay, as after. Okay, so this is your Jordan's lemma actually. So any integral that your exponential of I, you know, there may be infinite integrals that you're going to calculate. Most of the time in Fourier transform and all, you have that, right? That kind of integral, and in Fourier transform by nature is infinite integral, and you may have to calculate it over a semicircular arc or something. So in those cases, you can apply automatically Jordan's lemma. as long as the function by which, to which you're multiplying this factor, x1 I and z, that becomes 0 as z tends to infinity. Okay, that's the only condition. So what we have is f of z has to become 0 as z tends to infinity, which is the case for that example that we have, because we have exponent I z over z dz, which we have to calculate on 0 to pi, right? I mean, no, let me call it c to z. So m is equal to 1 in this case, and function is 1 over z in this case, so it will satisfy Jordan's law. Alright. So just don't arbitrarily write it as blunt as really you have to check, is it true or not? Okay? I mean, as I said, sometimes that's why you have to close the contour with the lower half plane. Okay, when you have an upper half plane. So those are things which will happen in some problem. So then your pole in the upper half plane and lower half plane, which pole you are using for calculation residue becomes important. So what's the time? I'm just trying to see. 6:10? 6:10. Okay, slow. Okay, let me do a problem on that uses multi-value function. How about the number? Let's see. So an example with an integrand is a multi-value function, multi-value complex function. So we want to calculate this integral, 0 to infinity, x to the power p minus 1 plus x dx. Okay, this is what we want to calculate. We're given this quantity p is between 0 and 1. Okay, this is real integral, of course. Okay. We have to prove this integral is pi over sine of p. This is what we have to do. Okay. So what is the complex function, complex integrand corresponding to this integral? This is my real integral, right? What is the integral that I will calculate? What should the integrand be? We're using the principles of complex variables for calculating real integrals. Okay, so our integrand we have to start with that. Just I want to calculate something like this, okay, some closed contour, right? And I'm to do this. Right? That's the simplest thing I can do. Okay, so instead of this is what we'll calculate, and from there we'll extract. Okay. Now the question is, what kind of contour I should choose, and where are the singularities, or what is the quirkiness of all my integrand that you have to evaluate. Now p is less than 1, so let us say p was half. Then what? You have z to the power negative, you have square root of z in the denominator, right? And I said anything like square root of z to the power 1 over half or 1 over 3, all of them are multi-valued functions. If you go around z equal to 0 and come back to the x-axis, it develops different values. In this case, it will develop 2 different values. Okay. So I cannot cross x equal to 0 axis, so I have to put a branch cut. That is one thing. Okay, so the numerator is giving me problem because it has z equal to 0 is a branch cut, and the integrand will develop if in a closed contour that goes around 0. It is going to develop 2 different values. Okay, that's one thing. The other thing is, what else is happening into this integral? What else can you tell me about this integral? That's a numerator, which is giving you a problem. What about the denominator? What is happening?
We have
Simple pole,
simple pole in
x
the
is equal
southern.
to minus 1. Okay. So in this case, my right hand side of the closed contour is not 0. It has to be 2 pi I times the residue of the integrand evaluated at z equal to minus 1. Okay, whatever contour you choose, supposing. So, and you go to 0 to infinity. So the way, I cannot make it as minus infinity to plus infinity because it is functional. It's not even functional at all. So, but at the same time, I need to avoid the contour that I will draw for such a case is as follows. Okay, this is your, that is equal to 0. This is a branch cut that we have introduced. Okay. So I'm going from, let's say this is the big circle is R, right? And let's say the small circle is radius small r. And so I'm going to go from A to B and come back here, and then I'm going to be going from in the clockwise direction here. The outside is counterclockwise, right? This is my C here has got different parts. C here has integral calculated from A to B. Then let's call that as a bigger circle C2, and this one is C1. You know, so you're going from 0 to 2 pi here, roughly, right? That's the integral, and then C to D, and the integral is, and then C1 equal to 2 pi I times, in this case, residue at, the function at x equal to, function z equal to minus 1. That we have to calculate. So don't forget the right hand side, okay, in this case, because, so we have, in this case, this is equal to 0, z equal to minus 1 is inside the bigger circle. Right? Okay, first tell me what is the residue. Let's calculate the right hand side in this case first. So, you know, what my integral, whatever it is at this point, I'm going to call it z. Okay. It's got all these parts we have to calculate. This is just to understand what we are trying to do. Alright, so what is the residue here? Use the notation a minus 1 because it's only 1, okay? At z equal to minus 1. So give me the right hand side, a minus 1. What was the formula? It's a simple pole. For simple pole, the calculation of formula is what? Simple pole at z equal to z naught. Then the formula to calculate residue is z minus z naught, f of z, limit z going to z naught. Which is what? In this case, z equal to minus 1, so z plus 1 times z is equal to minus 1. Our pole is z equal to minus 1. So I'm going to write it as, okay, let me just do it and then evaluate it. Z naught to got p minus 1 divided by 1 plus z equal to minus 1. Okay. So this and this I can cancel. So I have minus 1 to power p minus 1. And I can write minus 1 as exponential of ip, right? Cosine of pi is negative 1 to power p minus 1, right? okay, which is nothing but negative exponential of I y t. Okay. So my right hand, so that is your residue. So this is nothing but my right hand side is nothing but 2 pi I times residue, which is exponential I pi p, and the negative sign at this point. Okay, let's keep that negative sign. We'll have that later on. Okay, so that is my right hand side. Now let's get the left hand side done properly. Have you checked the, is it okay? My residues are all correct. Have you checked? Z plus 1 to Z minus 1 to the P minus 1, right? Minus 1 to the exponential negative pi is negative 1, so I put that there. Okay, so this negative is coming from the fact that I wrote it like this. Okay, and this is nothing but negative 1, and that's what is there. All right. Now, so on AB, so I'm going from A to B. On AB, my function is the following. No problem, right? On CD, I'll come to that in a minute, but what's happening on CD? If it was not a multivalued function, I would have written it as the same thing, right? When you come here, it has, x has become what? It has developed x will become exponential, this one will become exponential of 1 plus x. It has developed a factor of 2 pi, right? Exponential I theta. Theta is 2 pi when you go around once, right? So the phase factor has become 2 pi. And so this one, then I have is x 2 pi I to the power of p minus 1 dx. See, all along this, the value of the function is x, the integrand x power p minus 1, whereas along this, the value of the function is x times exponent, because r to power I theta, right? I mean, it has increased by that, and p minus 1, it will give me, it will not give the same value, it's going to give you a different value. Here, there's no problem, because that will be exactly 1 plus x. Because of p minus 1, it's not going to be there. I put it so that you understand that I've gone through one round, but the denominator, is 1 plus x. Okay, but I just want you to understand what I have done, that is developing this phase factor. Okay, so that is the main difference when you have a multivalued function. Then, of course, the rest is something we have already gone through. Plus, let's call that, going from 2 pi to 0, right? This function, let's understand this. Here there's no problem. I have part of p minus 1, 1 times exponential I theta, p minus 1, right? So basically on this circle, z is r exponential I theta. On the bigger circle, z variable is r I theta. So we'll do it in the limit r tending to 0. We'll see what happens to this integral now. It's not a piece of value integral, it's a different thing. So we have to understand this. R exponential I theta, and dz would become this f of z dz, right? Dz would be r exponential I theta I delta theta. I'm going from, in this case, 2 pi to 0. Plus 0 to 2 pi, that's in bigger circle now. R p minus 1 exponential I theta p minus 1 1 plus r exponential of I theta, r exponential of I theta, I day theta. So we're going to examine this integral in the limit r, big R going to infinity, and this one in the limit r going to 0, r going to 0. So what is this integrand? I mean, approximate this, okay? I mean, what happens to the integrand? R turning to 0, I think ignore this compared to that number, right? Okay, put it as 1. And I have R of P, and P is less than 1, that's understand, right? I mean, it's between 0 and 1. And this becomes exponential I theta P because I can calculate. So this integral is 2 pi on C1. What happens? 2 pi to 0, R of P, and I can, this is approximate, right? We are now estimating this integral. Exponential of I theta P, okay? And then I can take out, right, day theta. So for r tending to 0, this goes to 0. This is the integral which it goes to 0. Alright, if you look at it now, I mean, you can this can pull it out, but doesn't matter. You can evaluate that doesn't matter much, right? So it will go to 0. So there's no contribution, unlike the case of principal value integration minus I pi. There's no contribution in this case from this circle. What about the other one? R tending to infinity, I have to ignore 1 compared to that. So I have R exponential I theta in this case. So I will get that as for R of P in the numerator, and then exponential of the integrand looks like this, right? Exponential of I. I'm just looking at the integrand at this point. Here, exponential I theta. This is what my integrand has become. Okay. And so this is I theta P minus 1, problem. And I have R P minus 1, or this is less than 1, so maybe I have an R here, right? So I can put it as R 1 minus P if you want. Right? So if it's half, I have it in the denominator R tending to infinity, so it is still going to 0 in this case, okay, for R tending to infinity, because of the nature of the integrand. So all these things will, depend on the nature of the integrand, what happens with which ones, what will contribute. So this is also going to 0, okay, because you're ignoring 1 compared to R, it's large. So you're approximating the integrand and trying to estimate what it is going to be. And so both of them are not contributing, okay. So all we have is then the following. So A to B is 0 to R, in this case 1, right? C to D will be R to 0. R is the radius of the circle, and then R is tending to infinity. So this integrand is nothing but 0 to infinity. I'm going to flip that because I have a minus sign. So this is nothing but x for P minus 1, and then I will have that. Let's simplify that also. It looks like this, and let me simplify this. It's looking like 1 minus exponential of 2 pi I P minus 1. Okay. X of P minus 1 over 1 plus x dx. Okay, combining this term and that term. Okay, that factorize that out. And I'll have 1, because it's infinity to 0, I flip the limits. I p minus 1 is negative 2 by I exponential I by p. Okay, so this is what exponential of negative 2 by I is 1, so I don't have to worry about that. So this is nothing but 0 to infinity of x power p minus 1 over 1 plus x dx negative 2 by I exponential of I by p divided by this term is really nothing but 1 minus exponential of 2 by I p, because that's 1. Right? So what I have is here in the denominator 1 minus exponential of plus e by I p. That's what I have. Okay, let's see. So that is nothing but my right hand side is then okay, I'm going to pull exponential of I by p out. So that will give me 2I exponential I by p. Okay, if I put exponential of I by p out, I can have exponential negative I by p, because that will give me 1 minus exponential plus I by p. And this will cancel with that. Right? And on that I can absorb the negative sign inside, so I have nothing but exponential I by p divided by p, which is in the numerator, right? You have to check its if you want to convert it. So that is your sign pi over sign. This is nothing but sine pi p. Okay, so pi over sine of pi. Alright. So this is a problem. This is a case where, so whenever you have suppose x power half or something like that in numerator, denominator, or x power 1/3, you know that x equal to 0 or z equal to 0 is a branch point. So in this case, the integrand has z equal to 0 is a branch point, and z equal to -1 is a simple code. So you got two things happening in this case. Alright, and so since z equal to minus, it's not on the real axis, that's fine, it's inside the contour, so I can calculate the residue. It's in the bigger contour, right? I mean, this is what we are trying to do. So they calculate the residue at this point. In this case, we have to calculate. My right hand side is non-zero in the Cauchy residue theory. So this is non-zero, so you have to take into account that. And the only complication in this case is the value of the integrand along AB and CD are not the same, because, as I said, anything like 0 to the half, it is fine here, but when you come back, it becomes what r exponential of I, theta becomes 2 pi, theta is 2 pi, right? I mean, first time you're taking the square root of that. So it will become, on this, if it is square root of, it will be negative, it has a value negative r square root of r, whereas here it is. So if I put a circle like that, I will have a conflict, right? I mean, when it crosses, at this point, we'll not know which value to take. So because of that, we introduce a branch cut, it is about branch cuts. And we go around z to the 0 like that, so that we never cross the real axis in this case. That's how it is done. Branch cuts are introduced. So, if it is 0 1/3, maybe you got 3 different values, then we have z equal to 0. I mean, so you have many, many different values. So there's a conflict, and that conflict is resolved by putting this cut in the Riemann surface, and then in this case, the values, this was not the case when it was analytic function. Remember that when we did analytic function A, B, C, D, it's analytic, those would be the same. Analytic and single valued function, they should be exactly the same. It's only when the function is multi-valued, traversing the opposite direction in the same kind of segment, it will have different values. All right, I'll give you some problems this evening so that you can practice. I'll maybe do some more problems, different types of contours, so that you're comfortable, not necessarily, circle or semicircle. You can have other things, other rectangular or other things also. So I will, so that you are comfortable applying the Cauchy-Resty theorem. So that's what perhaps I'll do next time, maybe rational expressions in the denominator and all that, how to do it. And also maybe case with not simple pole, multiple poles are there, then you have to calculate residue carefully, right? And it's not just, you have to use a different formula for that calculation of residue. You have to take the derivatives, n minus 1 of the derivative, remember? Yeah. So I do not know the number, but just look at the back of the book index and go for complex variable or something. It will give you 26 or something like that. I don't remember, 26 or something like that. But I think sometime. Just look at complex variable, it will give you contour integration, it will give you the chapter number. I think it's 26. Okay, one more announcement. On Tuesday, we are going to cancel the class that is before the Thanksgiving, right? I mean, Wednesday is closed anyway, I think. There's no class on Wednesday. Wednesday, yeah, because day before Thanksgiving, it's just closed, right? And his classes are cancelled.
Yeah, classes are not supposed to be happening next Wednesday.
Yeah, right. So, but we are also cancelling Tuesday. Okay, my class is 5:30, 6:45, and we are going
Okay.
to go with the syllabus.
So we won't meet next week.
We are not meeting next week,
Yeah.
correct? Yeah, yeah,
Okay.
yeah. So tomorrow, Thursday we meet.
Mhm.
And
Yeah, Thursday we meet in for this week.
Thursday, yeah.
So
Day after
Thursday,
tomorrow we
yeah.
meet. We go over some more problems, many different types, I think.
Yeah.
So that you're comfortable applying the Cauchy-Resty theorem. Okay. Yeah, and I'll try to give you some problems maybe tonight, so that over the break you can practice contour integrations. It's simple if you
Our
understand the
first
concept.
test will be
Huh?
December 1st.
Yeah, test is on December 1st, yeah. So, the concept is fairly simple. I mean, all you have to know is, choose the right type of, contour, and why something goes to 0 or something, you understand. So if once I do a couple of different types of problems, I think you should feel comfortable applying it.
So the test is December 1st, and past that, we don't have anything else, because that's the last test for this, so class is over at that point.
Correct.
Is the final gonna be, same time and place?
Yeah. Simple class time, yeah. It's a test number 3. It's not final, it's, from whatever we covered from Fourier series, Fourier transform, Laplace transform, and complex analysis.
So we don't have any, when it comes to finals, we won't have anything.
Yeah. Only 3 tests, right? I mean, yeah.
We said something about that, I was under the impression that we would have this as a final or something like that, so that I wasn't expecting a test so soon.
No, yeah. Test number 3, right? It's on the syllabus, right? The date is exactly, it's on the syllabus.
Yeah.
The only reason I'm doing some of these things is just because it's just like, we should have one.
Yeah.
Yeah, for the voltage we just use the equivalent of 550 and then let's make the higher.
Yeah, all I want is what I as a function of T or something like that.
So just get rid of voltage and
No, but you could keep that, I mean, no, I'm not even giving any of them, I mean, I'm not giving what's impedance, nothing.
I see
You don't know anything, it's just, you don't know any physics, okay? You're seeing or solving this as a mathematical.
into
the dark, into the void.
Into the void, is the abyss.
I mean, you're given, you take it